Hello, good morning. I am Kalyan Chakravarti and from School of Electronic Sciences and Engineering. I'm here today to talk about fiber optic sensors, give you a gist of fiber optic sensors. Uh, to talk about initially, let me talk about fiber optical structure and optical fiber and its integral components. Uh, Fiber optic cable is made of a cable jacket, a strain relief aramide yarn, which can provide a physical and a physical, mechanical, and thermal protection to the optical fiber cable, which is embedded inside here. You have a cladding, and then you have a core. A cladding and a core are two integral parts of your fiber optic cable. You have a primary coating which also give a mechanical support and strength to your optical fiber cable. This being the basic structure of optical fiber cable. Now let us go on to the next important topic, which talks about the communication of optics or communication of light within the fiber optic cable. The basic principle behind the communication in optic fiber cable is total internal reflection. The total internal reflection is a phenomena which allows the light to be guided within the core and allows it not to transfer out of the cladding. That is, it always tries to provide a protection around the core in such a way that it doesn't escape or leak out. Now here, the idea behind explaining you the concepts of optical fiber beginning, though our topic is optical fiber or fiber optic sensors, we are going to talk about the optical fiber cable, its architecture, and then we're gonna go for its application as sensor. Here, the numerical, there's something called alpha here, an angle which when summed up you have 2 alpha. The angle talks about acceptance. This angle which is shared at the input of the optical fiber is called acceptance angle, and it has an angle of 2 alpha, wherein sine of alpha is given as square root of n1 square minus n2 square. Here n1 and n2 are refractive indices of core and cladding. The light travels through the core, but how does it travel through the core is always a question. Now there are the different paths and different methodologies which are followed by the light whenever it travels through the optical fiber are called as fiber modes. And the fiber modes are in turn dependent upon V number, which gives you the maximum number of modes that can travel through a optical fiber. Now this is just to tell you that light travels in all these kinds of fashions in optical fiber. Now coming to the actual concept of topic of the day, typical optical fiber sensing mechanism. When a sensor and a transducer, a sensor is a device which converts any such physical phenomena into an electrical quantity essentially, but a transducer can convert any such physical phenomena into another physical phenomena essentially not electrical. Now there's a statement here, all transducers can be called as sensors. All transducers are not sensors, but all sensors are transducers. Now when you talk about this statement, pay attention. All sensors are transducers because they convert one form of energy into another form of energy, but all transducers essentially don't give electrical output. So transducers are not sensors. Now here there are two kinds of measurements, a transmission measurement and a reflection measurement. A transmission measurement wherein light travels through the fiber and reaches the detector. That is, a whole communication channel is being established, a detector, a source, and a channel. For reflective measurement, you don't have the photodetector on the other side of the sensor. You have it on the same side of your source. Now you have light source traveling through the fiber, reaching the sensor and then comes back to the detector. Now this kind of reflection happening in a sensing equipment is called as reflective measurement, and the other one being your transmissive measurement. These two are two kinds of, I would say two arrangements wherein we can have a sensor system set up. Now here fiber being acting as a sensor, you should notice a fiber being acting as a sensor here. A sensing element is nothing but a fiber here. Generally, light is defined by all four parameters: its power, its intensity, wavelength, polarization, and phase. Now, any of these parameters can be used as our measurements, or they can be used as elements of sensing. Now, the basic procedure that is being followed in fiber optic sensor systems is being illustrated in this slide. You can observe Mr. Capron in 1970 has demonstrated the attenuation in light. Attenuation talks about the power intensity. Now, he said that the power intensity which is being received out of fused silica fiber was low enough that long transmission links were possible. Higher is the length, more will be the attenuation, and less would be the optical power that is being dissipated. Now, this concept was talked about in 1970 by Capron. Now, I would say the same principle could be used to make the fused silica optical fiber act as an optical fiber sensor. Now, how does the procedure goes on? Now, initially you need a source which can transmit a light along an optical fiber to a sensor, which senses only the change of a desired environmental parameter. This environmental parameter can be any physical parameter like strain. It can be strain, it can be temperature, it can be also strain, stress, and many other parameters. Now, the light refers to any kind of light. It can be an LED, light from an LED or a laser source. The sensor modulates the characteristics like intensity, wavelength, amplitude, and phase. All those four parameters which generally characterize the optics, which optical beam. The modulated light signal, I call it as a modulated light signal because its parameter, the light's parameter, after it encounters the environmental parameter, changes, and this change refers to the modulation that happens in the light. The modulated light is transmitted from sensor to the signal processor and then converted into a signal. The process of converting a modulated light into a signal is conventionally called as signal conditioning, optical signal conditioning, that is processed in a control system. And thereon, the properties of light involved in fiber optic sensors generally are reflection, refraction, interference, and grating. When I talk about reflection, there can be some part of light that can come back. Refraction, some part of it which can bend and escape. Some part of it which can interfere, that is, two light sources can interfere to give you a sensing atmosphere. And a grating. We'll talk about this grating in the next slides. When I talk about optical fibers generally, referring to my first slide, optical fibers generally come with a size of 125, 90, 50, 62.5 to 125 micrometer. Now, when I say 125 micrometer, it can be as thin as a hair follicle. Now, the major challenge one faces is coupling the light from a laser or any light source into the optical fiber cable. Now, when I do that, the problem is there can be all the essential modes I've been talking about. Generally the optical power is always protected within the modes, and at the center of a mode you have the maximum optical power concentrated. Now, when you don't have a proper coupling mechanism which can guide the whole of the light into a fiber, you have very little amount of it getting into the fiber and more of it getting escaped. Now, that should be taken care of in order to have the whole amount of light to get into the fiber. Now, in order to do that, you should ensure that the coupling efficiency is always 1. Coupling efficiency is always 1. Your multi-mode fiber coupling has to be avoided. It's always senseful to use a single mode fiber, because when you have multi-mode fibers, you have optical power dissipated and distributed among many modes. And when I talk about single mode fiber, you have only one mode of optical mode that is traveling through the fiber, with the maximum intensity concentrated in it. Now that is a sensible way. It's a sensible way to have an SM fiber, a single mode fiber, rather than an MM fiber. Now when you have a coupling between SM fiber and MM fiber, there's a question for you. If light is propagated from SM fiber to MM fiber, what mode can propagate into MM fiber? Obviously it would be one mode, which is nothing but a single mode fiber, because single mode starts guiding it guides a light or optical mode into a multi-mode fiber. So obviously only one mode will be getting into the multi-mode fiber. Now that should be taken care of. So that the idea behind this slide is you will have to have almost all the amount of power that you generate out of optical source getting guided into an optical fiber cable. Now that is very important. A light distribution in SMF, you generally have, that is what I've been talking about. The optical power, if you can observe, is maximum at your midpoint and tends to slowly decrease towards its origin, towards the border of the core. Now you can see IR, the current, that is optical current, that is concentrated in the optical fiber, is an exponential function of its coarse radius, a mode field radius. Mode field radius, the fields, modes, radius and optical intensity are exponentially connected. Now this is a general coupling mechanism which generally we employ to have the light guided into the fiber. Laser, you have a lens which can guide the light into the fiber. The optical fiber sensor. Now when we talk about an optical fiber sensor, let us talk about its definition. If sensor that measures, something that can convert anything into electrical signal, that measures a physical quantity based on its modulation of intensity, spectrum, phase, polarization and traveling through an optical fiber. Now here when I talk about intensity, spectrum refers to wavelength, phase refers to the angle, and the polarization angle. Now here when we talk about these four parameters that are concerned with optical fiber sensor, you should observe that these are the parameters that are being changed in the optical fiber in order to modulate the light which travels through the fiber, through the sensing media and reaches the detector. Now the basic advantages of using optical fibers, they are light in weight and compact in size, multifunctional, you can use the same fiber to sense many sensing parameters, remotely accessible, even to harsh environments you can reach them. You can reach harsh environments with them. Multiplexing, you can go for combining the sensing signals. Resistant to harsh environment. Immunity, resistant to harsh environment. It is resistance to it's made of silica which has got a melting point somewhere greater than 800 degrees Celsius. So obviously it offers a thermal resistance to the fiber. So it can reach even harsh environments. Immunity to electromagnetic interference. It doesn't have any metal parts in it, so it doesn't have any electromagnetic interference in it. Now those are the basic advantages of optical fiber. So there are two types of optical fiber sensors, one being intrinsic and other being extrinsic. An intrinsic fiber will have the fiber itself exposed to the environment. Here the optical fiber acts as a transducer. In extrinsic fiber optic sensor, the light source travels through the fiber, goes to an equipment which can modulate the light and thereon gets back. So here the fiber is itself not participating in the sensing activity. It's the element, it's the measuring element which is participating in the activity of sensing, and the light which is being modulated travels through the optical fiber. Now there is no direct interaction between the environment signal and the fiber in extrinsic fiber optic sensor. In intrinsic, yes, you do have an interaction between environmental signal and the fiber optic cable. That is the basic difference between these are the definitions which say extrinsic, the fiber carries the light from the source to the detector, but the modulation occurs outside the fiber, wherein it takes place within the fiber in intrinsic type of optical fiber sensor. Now optical fiber sensor sensing mechanism. The sensing mechanism can be of different types. It can be point sensor, it can be either multiplex sensor or a distributed sensor. The point sensor, a sensing element is only one and it's going to only sense one particular parameter. Now multiplex sensor, yes, you may have many other sensing equipments, one optical fiber which can respond to many kinds of physical quantities, and it gives you the outputs of many physical quantities. Distributed sensor, you can have one sensing parameter but distributed over a whole zone. The sensing is distributed along the length of the fiber, throughout the fiber. Multiplexed, only some regions. Point, only one point or in the vicinity. What all can we measure using an optical fiber sensor? The physical quantities like temperature, pressure, strain, displacement, acceleration, so on to rotation rate. All these parameters are physical quantities which can be converted into their electrical equivalents using fiber optic sensors. Now how do you do that? Let us now only talk about amplitude and intensity based sensors. An amplitude and intensity based sensor, amplitude here refers to, amplitude of an optical fiber refers to intensity of the light which is being carried by the optical fiber cable. Now amplitude and intensity based sensors are predominantly used for pressure and strain measurements. When I talk about pressure and strain measurements, it is the force that is exerted on the environment, within the environment. Now that force or weight or load can be measured using optical fiber. That's the idea. Now here intensity based sensors are conventionally intrinsic sensors, wherein they have this fiber optic cable being affected and interacting with an environment signal. Now the environment being a pressurized environment here, look at this architecture. You have a deformer 2 and a rigid support. Deformer 1, which is protruding, which is corrugated, has got a table or a base or a rigid support, or sometimes also a biometallic strip, which is being exposed to the pressurized atmosphere. When the pressure tends to fall on deformer 1, you have it being suppressed on deformer 2, while you have an optical fiber cable that is carrying the light from source to the detector through it. Now when the deformation happens, you see a physical deformation happening at the teeth's interaction between two deformers, wherein the diameter of the cladding is disturbed and it undergoes a physical deformation. This physical deformation always allows the light which is being traveling through the core to escape. Because the N1, because you know the total internal reflection is dependent upon N1 and N2, and when N1 is subjected to a refractive index change, you have the total internal reflection also being disturbed, because of which the light tends to escape. Now the light intensity which is being escaping here is directly proportional to the pressure you apply on the deformer 1. Now here you see the waveform will initially have the maximum intensity of power when you don't have any pressure being exerted, and the minimum of it when the whole of it is being exerted on deformer 1. Now that is nothing but you being converting the pressure onto its electrical equivalent using the optical fiber cable. These systems generally have a poor range and poor ability to screen the noise, leading to the lower precision. The precision, how accurate it is, how right the value is, but are simple. They are simple to manufacture and quite inexpensive also. So you can also the same intensity based sensors can also be used for displacement. This is one of those applications which can be used to measure the displacement. When I talk about displacement, here look at this diagram. The moving target moves from fiber 1 to fiber 2. You have the light being dissipated from fiber optic cable 1, and it's been intensified onto the moving target, and thereon it reflects back. This kind of measurement is reflective measurement, and when you have the target moving from position 1 to position 2, you have the intensity reduced within the detector. Now, the amount of electrical equivalent you receive on detector is directly proportional to the movement of the target. Now, this is one of those intensity based measurements. I think I am done.
Press F10.